Okay, now looking at this example, first of all, again, we need to know what our domain of this function is. And of course, the fact that you have the rational exponents, that's what keeps this from actually being a polynomial. But since your denominator is a 3, if you remember, that would mean the same thing as a cube root. And like, you don't ever have to worry about those issues of, having an even root of a negative, which ends up producing imaginary. So like in this case, your domain would be negative infinity to positive infinity. Okay, so first of all, we need to do our first derivative, and you would just do that based on your power rule. But what you're going to end up with after you do your power rule, and you would have a common factor that you could factor out, this is what you're going to be left with for your first derivative. Okay, so originally, this would have been distributed through here, and what I've done is this was the greatest common factor, so I have factored this out. Okay, so from here you're going to get your critical numbers, and that's going to be the values that are going to cause this to equal 0. So you have your 10/3 x to the 1/3, set it equal to 0, and solve this. Then you're going to end up with x equals 0. And then we have x to the 1/3 minus 2. If you set this equal to 0 and solve it, of course, this being a 1/3 power, that's the same thing as cube root. Then what you're going to need to do is cube both sides. Therefore, you're going to get x is equal to 8. So when you do your number line or your sign graph, of course, this is going to be for your first derivative. Then we'll have 0 and 8. And we've got to pick our test numbers for each of those sections. So I'm just going to use -1, +1, and 9. Now remember, you're going to substitute the test values back into the first derivative. So if you were to substitute -1 into your first derivative, then you will receive a positive value. If you substitute +1 into the first derivative, then you'll have a negative value. And then substitute +9, then you're going to have a positive value. So that means that what we're dealing with is this is a section that's increasing, this is decreasing, and this is increasing. So you could go ahead and identify those intervals. So you're increasing from negative infinity to 0, and you're also increasing from 8 to positive infinity. And then for decreasing, that would be, of course, this middle section that runs from 0 to 8. Now also from this you can determine, if you remember, your maxes and your mins, your extrema. So if you have a section that's increasing and then decreasing, then that means here at x equals 0 you're going to have a max, and then if you're decreasing and then increasing, then at 8 you're going to have a minimum value. Now, those are actual points on your graph, so you will need to substitute the 0 and the 8 back into the original function. So if you substitute 0 into the original function, then you're going to get 0. So that would be the 0.00, which is a max. And then substitute the 8 back into the original function, and that's going to give you a value of -16. So the 0.8 -16 is going to be a min. Okay, so that'll be all the information that we can get from our first derivative. Okay, so next you need to find your second derivative. Now, when you go to find your second derivative, my suggestion would be, like, as soon, of course I didn't show all the steps in here, remember, to save some time with the video, but I wouldn't use this form of the derivative because this would require product rule. I would go back to like this first step here, like as soon as you have gone through the power rule, even before you bother to start rewriting it and doing all the factoring, I would use that form of it to get the second derivative, because then that way it would just be power rule again, okay? Now, once you get that, and again, you'll have to go through some steps of rewriting, what you're going to end up with would be this. Okay, so that's what you should end with for your second derivative. Okay, you do have a common factor, of course, on top of 20, but on top, yes, of 20, and you could factor it out if you chose to do so. Okay, so now from here we need to find out what values cause this to equal 0 and what causes it undefined. So it's going to equal 0 when the top equals 0. It's going to be undefined when the bottom is equal to 0. So if we take our 20x to the 1/3 minus 20, set it equal to 0 and solve it, then you are going to end up with, of course this would be 20x to the 1/3 is equal to 20. So x to the 1/3 is equal to 1. Cube both sides, so of course 1 cubed is still just 1. And then if you take your 9x to the 2/3 equals 0, then you're going to end up with x equals 0. Okay, so those will be the values that we're going to use on the sine graph for our second derivative. And then you'll want to pick a test number again in each of those sections. So we'll use -1, 1/2, and +2. All right, so you're going to substitute these test values, remember, back into your second derivative. So what you're going to end up with is actually this section's negative, this section is negative, this section is positive. Now, of course, most of the time your signs alternate. That's just what's most common, but obviously it does not have to. So this is a section that's concave down, concave down, concave up. All right, so let's identify those intervals. So concave up would be from 1 to positive infinity, and then concave down. Now, since these two sections or intervals are right next to each other, sometimes you can lump them into one and sometimes you can't. That's going to vary from problem to problem, and that is based on your domain. Since my domain was all real numbers, that means that 0 can be included. Therefore, I would have concave down from -infinity all the way to the +1. Now, I would have to leave it separate intervals if the 0 had to be excluded from my domain, okay? Now, points of inflection, if you remember, points of inflection are going to occur where the concavity changes, and the only place my concavity changes is here at +1. So with your points of inflection, so we know that's going to occur at x equal 1, but you're going to substitute the 1, remember, back into the original function because it is an actual point on the graph, which is going to give you -3. So we've got the point 1, -3 for our point of inflection. Now, you're not going to have any asymptotes on this type of function, so nothing to worry about there. Now, x and y intercepts. Now, obviously, we know our y-intercept, and that's because back up here, you notice we have the point 0, 0. So that has to be my y-intercept. Of course, these are functions, so you can only have one y-intercept. But it's also an x-intercept. But there may also be other x-intercepts, okay? And actually, you do have another one here. It's not one that's real easy just to find by hand. You know, so just use your calculator to help you with that. But what we have for our x-intercept, again, is 0, 0. But we also have, and I'm just going to round this off and say it's about 15.6, just because in graphing this, I can't be any more precise than just one decimal place anyway. And of course, the y-intercept, as we said, is also at 0, 0. Okay, now, in graphing this, using all of this information to sketch the graph, Okay, now if you remember, I have the x-intercept that's at 15, so we do need to do several tick marks out on our x-axis. Actually, I think I'll do these by twos. So 2, 4, 6, 8, 10, 12, 14, 16, just so we don't have so many tick marks to do. Now we had a min that was at 8, -16, so I'm going to do that by twos as well. So 2, 4, 6, 8, 10, 12, 14, and 16. So I had to put those just a little bit closer together, but that's fine. Okay, so we had 0, 0, and 8, -16, 2, 4, 6, 8, -16. We also had an x-intercept that was at 15.6, so 2, 4, 6, 8, 10, 12, 14, so 15.6, we'll just call it somewhere right in here. And let's see, we also had the point of inflection that was the 0.13. So let's mark that. So 1, 3 would be here. Okay. So I've got all the points here. Now, that's not a point, that was just a blob that was on my piece of paper. But this is where your increasing and decreasing can come in. If you go back up, the negative infinity to 0 was increasing. So starting on the left, you're going to increase until you get to x equals 0. But then from the 0 over here to the 8, you've got to decrease. Okay, so this is going to come down to here. Now remember, this was actually a minimum value, so I know it's going to dip down and then it's going to come back up, because after you leave the 8, it goes back to a graph that's increasing, and then it just continues to climb from there, because you're increasing, if you remember, goes all the way, continues to the right forever with positive infinity. So that's going to be the sketch of your graph here.